Okay, so let me make sure I get everything right that I actually need to do today. Sorry, you guys' class confuses me sometimes because I just fit two into one. So the first section of this is going to be talking about adders. The second section is going to be multipliers, and the third is going to be state machine charts. So we use state machine graphs. These are state machine charts. State machine charts, which we'll get into, are just a more annoying way of drawing state machine graphs. They're more specific. But we'll start with adders. So what terrible marker should I start with today? No, I need to do this, be seen by this thing. So I have like red, well, really green and black are my best options. Purple might be okay. One of these days I'll actually buy, there we go, purple's great. Okay, so. Yeah, I probably can, but adders. You guys learned about full adders way back in 2700, right? Where a full adder is just a term for something that adds A plus B, has a carry in and a carry out. So if we want to start off designing a full adder, we have this nice tool that we can do where we know we have inputs A, input B, and input C, right? We can start designing a truth table. And this is actually a really terrible way to do it. Let's reverse these. A, B, and C. Good, I'm actually in count. Right, so I have a truth table, and we just want to add them up. Where C is the carry in. C in. And the output is both, we have a sum and a carry out. Right, and so the sum is nice and easy, where we just go 0, 1, 1. Well, it turns out this is 0, right? And then back to 1, 0, 1, oh, 0, 1. Right, and then the carry out just happens on any time that we have 2 1s and or even 3 1s. Right? 1, 1, 0, 0. Okay. That's all the full adder is doing as far as the truth table goes, right? So what we can see from that is that if you take the expression for this and say throw it into a K-map or something, because I'm going to save the effort of going through that, you're going to end up with an expression that looks something like, I'll make sure I don't get this wrong. This is equal to A, B, C. I'm just writing C for seeing. Right, so that's just stolen directly from the truth table. There are four terms. This happens to simplify down into C. I'll make sure I get this right. I did this derivation earlier, which is fun. There's one more bar on this one. This one? Yeah, which is what I'm building up to. So this starts to get nice. We've done the full ladder, we know that it's pretty much just an XOR operation. The whole point of this is to get to Y, because this helps us when we start building up a more complicated adder, right? Because we know what ripple carry adder is. And the ripple carry has, well, first off, does anyone not know the ripple carry? Everyone's familiar? You don't? So the ripple carry is just you take a full ladder and then you string a series of them together where the carry out is tied into the carry in of the next. And then the downside is that when I upload new inputs, it can't know the answer until the carries have carried all the way through. So if I have 32 bits that I want to add, I have to carry through 32 carries. So if I have 2 gate delays, say in a full ladder, which is possible, right? This would just be 2 gate delays. Then you would be in a situation where you have 2 times 32 delays. And so if you're running, no matter what your clock is, you can end up in pretty small limitation for how fast your adder can go. If you're trying to do complex algorithms, you may do a lot of addition, especially because we'll find out later, multiplication is really just addition, especially in binary. And so you want to do this fast. And that's what we're going to build up from this. And we're going to start with the basics of Y. So this one confuses a lot of people, both in 2700 and in this one. This does not equal 1. Right? A, B, or A, that is equal to 1. But this is different from that. And people forget that and causes them issues on exams. And what you'll find out pretty quick from this expression, if I do A and B, well, if I have AB or A bar B, I have a 1. Otherwise, it's 0. Similarly, over here, if I have not A and B, or A and not B, right? So in the first case, I have an X NOR. And in the second case, I have an X OR. Okay, so if I end up with that, X OR and X NOR, then we can simplify this to what? C and A X NOR B or C bar and X, oops, A X OR B. But now I'm back in a situation that is really nice, because all of this, well, let's just look at it. If I don't have C, it's just A XOR B. If I do have C, it's A XNOR B. So everything just kind of depends whether or not I have C, right? Or we can consider it the other direction. It ends up not mattering. So let's say that I do have an equation that I want to worry about just C, right? And then I can just end up with, and I know I want it to depend on A XOR B, because that would be really nice. So if I have C something A XOR B, it turns out that exclusively if I have C, or I have not C and this, I can just write it as C XOR A XOR B. Now, due to the order of operations, these parentheses don't matter. but it's helpful to visualize what's actually going on. Because if I exclusively have A or B, then C is what starts determining what my sum is, right? But if I have C, then in either of these cases, I need to start worrying about it. Because if C is 0, right, then I just have that. Any one of those zeros just simplifies down to the other two. So that's really nice. That's S. We can do a similar thing where our carry out is really just, well, this is a trick that they're going to use. The carry out, right, is just going to be if I have A, X, or B, if I use a half adder, right? Sorry, A and B, not X. The carry out is just A and B if I have a carry out. It's a little bit more complicated if I have a carry in, so it's a full adder. But we're going to use the fact that a half adder uses only A and B. Because we're building up to this idea that we can use a nice simple expression for each of the full adders that we would have in a ripple carry, and instead only worry about using gates to determine what our carry in and carry outs are going to be. So this is what we're building up to. It's called a carry look-ahead adder. So that in only a couple of steps, regardless of the number of bits we have, we can do 32 bits of addition in 3 gate delays. The downside is we're going to end up with a lot of logic to start implementing this type of equation. So let's introduce 2 more relatively simple ideas, where we're going to have 2 terms. We want to know if we're going to generate a carry or propagate a carry. So generate means that I myself am making it, right? So the full adder is saying that for I, this adder I is making by itself a carry. Propagate means that I have a carry coming into me and I'm pushing it out the other side. So it's propagating through the full adder. So if I generate an I using the half adder trick, well, and actually this is true in either one, really, but we'll focus on, right? Generate is just A and B. I know that I made one because I'm not having to worry about a carry in, because that gets handled by the propagators. So then the propagate needs to worry about, again, in the simplest case, A, X, or B. So now we can start stitching these together in relatively simple equations where I carry out of 0 is obvious, right? The first bit only depends on itself because it is a true half adder. So on P1, P1, G0, or P1, P0, and so on and so forth. So we can start developing these really complex equations to start looking ahead to see what our carries are actually going to be. And our sums, as we showed earlier, they already know. Because as soon as these carries are generated, it's just A, X, or B, X, or C, right? So in just a couple of steps, all I have to do is generate A and B, and then A, X, or B. The next step is to start generating this logic, in order to generate our carry. And then the third step is to do the AX or BX or C. Yeah.
Well, on that C1 term, what's the P0, C?
G0, P0, C1. Or, sorry, it might be C0. You probably did that. Sorry, let me double check.
Okay,
It's probably C in is my notes. Yeah, C in. That's what I forgot.
That makes more sense.
Yeah, sorry.
Thank you.
Yeah. And you'll just keep adding these terms as you make more and more of these. But you can see how this logic starts to cascade in complexity really quick. No, because this is only one gate. Because all of this is happening in parallel. It's OR and AND. Well, I guess this could be two gates, right? Because it's an OR and an AND. So we've got one gate delay, two gate delays, and then the final stage, which is the one gate delay. So in just 4 gate delays, we're done, regardless of how many bits we have. So this has a benefit of very fast, but very large. Yeah. No, P0 is the first full adder's propagate. This is PI. So GI, PI, where PI is AI, BI, where I can be 0 to N, the number of bits. No, it's just, well, yeah, you need a carry in for the first guy, just in case. Really, you could consider it not if you only want to design this out. The reason we want to carry in is now we would say only want to design 3 of these equations and then start sticking them together and write a fairly simple output, which is as simple as, well, the carry out. So in order to do a 4-bit, I would normally need to see 3 of these equations. All I need to carry out is a 4th one of basically that. And now I have a carry in and a carry out, and I can just start sticking them together with only a little bit of extra overhead for the carry out, as opposed to just building it all in one chunk.
So why is there a delay in search? If each one depends on the previous.
So because this one doesn't depend on C0, it only depends on the carry in, which is available from the get-go. Yeah. So you can, and they do very frequently, design these up in 4 or 8-bit blocks, and then I will have a little bit of delay, right? So I'll have a mixture between the look ahead and the ripple. So I'll have chunks of look aheads and then ripple through those look aheads. But still, regardless, it's going to be much faster to implement a 4-bit one of these and then ripple it through, right? It's 4 times faster or something. Yeah. Yes.
Well, I guess I'm just a bit confused. Because don't we still need to calculate the B and C?
They're available right at the very beginning, because A and B is available in both cases.
So
Well, you're not going to add 3 variables together, right?
No, C period.
C3?
Yeah.
Oh,
C3
G2 or P2, G1, oh, sorry, P2, P1, D1, or P1, oh shoot, there's also P0. All right, this is why they're awful. Or P0, P2, P1, P0, P1, P0, G0, or I will just double check so I don't screw this up. Oh, they don't even tell me because it's awful. And you keep going with these reductions until you get down to 2n or something like that. This I'm not 100% sure on. Gonna have to go back through and figure out the math. I only derived so far as this, so. But it is available in your book. The book spells it out explicitly. I'm deviating from the book to different notes because I did the notes. I used the book class for the Monday night, and they got screwed. It was not a very good lecture. But really, you'd only ever look this equation up. I'm never going to expect you to like memorize this equation. That's insane. But the takeaway is that I can just count these C's and just kind of skip ahead and not have to ripple them through, and then stitch them together and still have a better carry adder. So that's what a carry look-ahead adder is. There are actually more algorithms than that for the multiplication. And the nice thing is, and we'll talk about this with multipliers, which I think is next. Yeah. So what will happen in reality for most of you? If you end up designing something in an FPGA, you're not going to write out all of this. This is mostly helpful to be aware of how they're implemented. What you're really going to do is go use what's called an IP core, which I will introduce you in the current lab we're working on after I upload part 2, which is tools that they use in Vivado, Quartus, or Lattice is another one, where they provide you nice, easy mathematical blocks. And these are going to be mapped to FPGA, what we call fabric, right? The fundamentals of the block in math cores, essentially, where the FPGA itself is built to do math. So that these complex algorithms to do adding that are pre-built for you. But this is still a very complex idea and very important. You might someday be asked something about this in an interview, because interviewers ask the dumbest questions in digital systems. Job interviews, they're really terrible. I mean, I've had some dumb ones. I wish I could remember right now. I had one, they asked me a question and I walked out. I was like, if that's important to you, then I don't care to work here. Sorry, I just can't remember what it was. It just so annoyed me. I had another one. No, I can't, because like it'll pop up to me at some point, I'm sure, like right after you guys leave. But they're usually, the ones that I hate are anything that are like, what kind of tree are you? And I'm like, I don't care. That's a real question my girlfriend got asked me for the interview of her current job. What kind of tree are you? Like but I had one that if basically for on semiconductor, they handed me basically what looked like the 2700 exam. It was just like, here's a packet, solve these problems. And it's like, okay. Okay, so multipliers. These are really important, right? We multiply things all the time, and you can build most circuits off of adders, multipliers, and then you need to integrate and differentiate. It turns out that integrating and differentiating is really easy in digital systems and analog systems, actually. So multiplication, both in analog and digital, is very difficult, or would be, except for some handy algorithms. So the general idea is that you can do multipliers a couple different ways. You could build a combinational multiplier, which is where we draw out the truth table, right, and we draw out some circuits, and it has inputs and outputs, and da-da, we're done. The problem with these are they're huge, they're big. They're very fast, they only need a couple of gates, but they're very big. You can do sequential circuits where you just kind of step through into each individual bit. These can be very small, right? It's basically just a state machine. These are slow, but they're very size efficient. If you need really, really fast, you can use a ROM, right? You can just put all possible values of the multiplication for every bits you have, and then it's just look it up. Here's my input. What is my answer? This has the benefit of it's very fast, right? It's one clock cycle and you have your answer. Again, these scale horribly. They're huge. The last one is what we would call hard multipliers. And these are ones that are built into the fabric of the FPGA. And you would access this using an IP core. What we're going to talk about so that we understand multiplication from a digital standpoint is the sequential ones, the ones that are state machines. We've been talking a lot about state machines. They're pretty important. So let's say we want to multiply this, right? So much like our decimal multiplication, well, identical towards multiplication, what we can do is just consider each individual component of the multiplier, that's this guy, and multiply it by the multiplicand, I think that's what they call it, but it's a multiplier, multiplicand, and then just start adding them together. So I do 1 times 1 is 1. 1 times 0 is 0, 0, 1. Then I step over 1. 0 times anything is zeros. Then I step over 2, because I'm now in probably the hundreds bit. And then it's just going to be 1, 0, 0, 1, but shifted. And then I can add these up together. 1, 0, 1, 1, 0, 1.
Yeah.
And so this is 9, 5, and then I'm pretty sure that adds up to 45. All right, we can figure that 32, 45. Yep. Right, so that's multiplication. Now you're going to notice something. Well, maybe not, but this is what some very smart people notice. That every time you do this, you're really just only ever taking the multiplicand and just moving it over if there's a 1.
Yeah.
So this gave rise to what they call the shift and add method, where literally they just shift it and add it if there's a 1 here. So that's the brute force way of doing it, absolutely. But fortunately, there are people that are smarter than you and I, and they came up with this lovely idea. So let's say we want to multiply two 4-bit numbers, and I only ever have to add 4 at a time, right? Because they're only ever going to be 4 bits. So let's make a 4-bit adder. And then we're going to create a nice buffer. No. So this is what they call the accumulator. And all it's going to do is it's going to take an accumulation of the sums that it needs. And it's just going to pull out whatever it needs. Let's see. Wow, I actually wrote the right number. And so say that there was a 1 here, like so. What it's going to do is take an input that is just the multiplier, right? And it's just going to shift through those. And if there's a 1 here, then it can add the multiplier or the multiplicand back into this, and then just shift 1 over. And if it's a 0, just shift. There's a 1, add, and then shift. So that's all it's ever doing is adding or not, and then shifting, and then adding or not, and then shifting. And it only has to do that a couple of times, really the n bits, right, before you get the right amount. And because you can add each of these individually, right, so we went and created a stack of 3, and we went through and added all 3 up. This is just adding them one at a time, and that's why it's called an accumulator, because it's going to do each add at one step. So now all you need is an 8-bit buffer, a 4-bit adder, and a little bit of support logic. If you multiply 4 bits by 4 bits, you get 8 bits at most.
So if you wanted to divide it, you add 1 more on the add.
Well, no, because you will never get. Oh, I see what you're saying. Into the accumulator. Yeah. So if you want to do 5 times 5, then you need the sum of those two as the output. So you want 5 bits times 5 bits, then I need 2 additional bits in my accumulator.
So do they need to do the same, like when you can't multiply by?
You can absolutely. I mean, we just did it, right? You can absolutely multiply 4 and 3. Not a problem. It just so happens that people like to use 4-bit adders as the foundation for everything. And well, I won't go into it because I don't think it's that helpful. But you can start stringing these multipliers together. So you can start seeing how you use little blocks to start building up really complex algorithms. Every once in a while, like for extreme optimization, you want to build an 8-bit adder or a 12-bit adder or something in order to make it a little bit better. But that's the shift and multiply. Sorry, I got to make sure that I'm not skipping anything. This feels like it's going by way too fast. It takes a lot longer to remind myself how to do things than it does to just explain it, doesn't it? Oh, that's what I forgot. That's fine. It's a good transition. Everybody get the shift and add. There's the example in your book. There's actually a whole bunch of other ones that can do for multipliers in there. Actually, there's going to be one more, isn't there? But it's stupid. And by stupid, I just mean easy. This is what they call the array multiplier. The array multiplier is really easy. It just takes the advantage of the fact that we have a cascade of additions, and it uses the similar logic to the carry look ahead. This is page 217, if you want to look. There's probably an easy way to do this. It just requires, I hate drawing a million gates, you know? I'm really bad at this, like looking up and looking down thing. X 0, Y 1. I need one more set of these just to make it clear, and I'll stop with that in a minute. I'm going to stop there. I think it can be clearer if it's not all cleaned up. So this is just the brute force method of doing it. This is just an array multiplier, right? Where I'm starting to take, if I have x0 and y0, my lowest place, p0, product 0, is just 1, right? And then for each of those, I do x1 and y0, and x2 and y0, and then x3 and y0. And then I'll do x1 and x0, y1, right? And I'll just have inputs for all of the x's and the y's, and they'll all go just cascade through a million full adders, and they'll work. So this has a little bit of benefit over some of the other options. Big benefit, it's very fast, right? There's no clock. There's no shift and then add and then shift and then add. It's just a cascade of gate delays, which is generally faster than your clock is going to be going. The downside, again, I mean, it gets huge. It's a massive clock. But they work really well. This one is not clever, like the shift. Yes. Yes. The shift one is going to be built off of a state machine. Because your state, and we'll actually get into building one of those in just a moment, because they're pretty interesting. But I need to take a step back because I almost forgot one of the parts of this. I'm going to ask, is anyone confused on anything I've done up here so far? Because I feel like it's going really fast. We're going to end up getting out early today, so I'll just take a breather, see if everyone's doing okay. And we're going to bounce back to something called debouncing, which is a section I just forgot. Yeah. So debouncing is an issue, well, a solution to a problem that we get in the real world. So if you and I push a button, right, and our FPGA is running at 100 megahertz. Compared to us, that clock is very fast. So if I have a counter that's trying to count the number of button pushes I do, and I just touch it and let go as fast as I can, there's two different problems we could run into. Both of these are kind of debouncing problems. The first is if it's just a clock running and it's trying to see if this is 1 on my clock, let's add to the counter. Well, that issue is going to be, I'm going to push it and let go. And no matter how fast I do that, it's still going to be a couple milliseconds, maybe, right? And that clock at 100 megahertz is going to count from 0 to 180 or whatever it ends up being, right? Just like, ding, 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 and we're like, oh, well, I didn't do very good at that. The other issue is that these buttons are real physical devices. So we would like to think that they go click, click when I push it. They don't. What really happens is they go click, click, and then we end up with bounce. So what we would like to see is off to on. What we really see is like so. So there's another issue. I push that, and I have a state machine that is watching that says, on the rising edge, add 1 to my counter if this button is pushed, right? So it sees a rising edge, and then goes, oh, let's take a sample, and then samples this. So it thinks it's trying to get a 1, but it really just got a 0. You guys may actually encounter this on your board when you're doing the little switches, right, to control the most significant bits of your DAC. You throw a switch, and if you have a process that's just watching for a change in the switches, you throw that switch, it's going to go change, 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 right? And depending how the rest of that state machine is, it might just go change, take it, and then have to go through some other state machine stuff, and then come back, and then you end up with a 0, and it looks wrong. So a couple ways of dealing with this. Well, the first one is a hardware solution, right? We could put a filter on this so that it can't just go up and down. You throw the switch and it just kind of wanders up to that level. The downside to this is obvious twofold, is that, sorry, this should just be a flat. Right, so I throw my switch and it has to charge up some RC circuit. Downside is now I have to have an RC circuit. So I've just added size. The other issue is it actually ends up having to be quite a bit slower than your circuit does. The last issue is in a real sampling system, right, there might be some region that it decides between high and low, right? Because there's a comparator that decides if it's on or off. And if it is on, this gets really messy. Let's see if I can do this right though. So this is the switch that I have to go below to turn on. Or sorry, I have to come over this to turn on. Over this threshold to go on, under this threshold to go back off. This is kind of an ideal situation because once I cross that, I'm never going to kind of come back under that. But if it's flipped and there's this kind of no man's land, I could literally end up with some internal oscillation because the comparator doesn't know what it's supposed to be. It doesn't help that these transition points are dependent upon the power supply. And if you throw lots of switches at once, the power supply can actually dip. And then you'll end up in a weird situation. We don't like that. Not very good solution. A good solution then is, well, there's two of them really. One of them, the method that we might use because we love state machines, let's design a state machine. It detects a rising edge, waits for a little while, and then samples, right? The other one is do that exact same thing. I just always call it the click count sample method. So you click your switch, you count for a little while, and then you sample. It's very similar to the state machine method, it's just it uses a counter instead of a state machine tool. Yeah. That is actually a method that you will see as well, is not just one flip-flop, because the first flip-flop can latch in a bad value. You can actually, and the book covers this more in detail. I don't use this one very often, but you can actually just chain a couple of flip-flops together, sometimes just two, and that clocking it in, that the chain flip-flops add a level of stability that will make sure that you don't end up swapping back and forth and seeing this on this. That's debouncing. It's mostly just an issue to be aware of, and you will run into at some point. It's a very easy solution. And you will probably, honestly, a lot of times if you go work at a big company, they'll just hand you a package of pre-written VHDL. And like anytime you interface a button, you do it through this module. It'll be called like push button or dip switch or whatever, and you just throw that on at any of your outputs or inputs. But an issue to be aware of so that if you get asked of bouncing and someone asks you how you solve debouncing, you could be like, I would use a state machine to wait for the bouncing to be over and then take the sample of what it's supposed to be. Yeah.
Can you also sample such that you won't have an issue?
Well, that's what the two things are doing, is just methods of waiting until this point to sample. And your data sheet for the switch should have information on its maximum bounce time. Switch data sheets are awful. I will tell you this. They're not very consistent, but it should have that. And if not, if you're a big company, you'll have access to a mechanical engineer and they'll tell you the answer. The other way is you can get a really high speed like oscilloscope and just start throwing a switch and watch it bounce. That's how I do it almost every time. Is I use it. I don't know what it probably has a real name. I just say click count sample because that's how I do it, and it's super easy. Yep. about right, yeah. Yeah, and one of the places that you might be, depending on your sports cheering for, is that the digital score counters for basketball hoops, they have a debouncer because they don't want the score to go weird if the basketball goes halfway in and goes and down, because that can trigger like a million points. In fact, at my old high school, they had one of those that would do that. If you shot it just right, it pointed it. But yeah. Long time, yeah. Okay, so that was those array multipliers. We're going to get onto state machine charts, which is, we're going to talk about these array multipliers. Let me make sure I do this in a competent order. Yeah. So state machine charts take the idea of the state machine graphs. So I'm just going to start saying SM charts, SM graphs. So SM charts take the idea of an SM graph and make it more complicated. So it's going to have really 3 different symbols. And I'm going to be honest, I never use these in industry. I use more of the, well, if you take any like of the advanced software engineering courses, you might see some of the software systems engineering diagrams that are a little bit more abstract. This is the opposite of abstract. There is very little abstraction in this. If you get a square like that, this is just what we would call a state box. This is the first thing that happens when we enter one of these charts, and it would say like, hello, I'm state 0, and I'm going to output Z1 is high. So anytime I'm in state 0, Z1 is high. The next thing that they have is conditional statements. And you've probably seen something like this in junior high, where there was like some flow chart to find out which Harry Potter character you were. I can't fit condition in there. The other one, you'll see like an XKCD cartoon will tell you how screwed you are, or like what career should you go into, right? The symbol is pretty common. Basically, it comes in here and then says, depending on what the condition is, whether 0, 1, go somewhere else. The last one is a circle. So this is just outputs. If I put like Z1 in here or something, so this happens every time I enter the state. This can be like some extraneous, oh, I need to change Z4. Or it could be like, hey, ready has to happen. So we can start chaining those things together to get, and I'm just going to start from here. Because the rule of SM charts is that they're going to, I hate these things. So they build these as little blocks, and they expect you to design a VHDL for each of these little blocks individually and then start stitching them together. In my experience, this ends up with really bloated code because you have to build a million modules, and I don't like it. But it can be helpful to think through, and this may be a useful tool for someone else. So I think it is worth teaching because not everybody has the same way of thinking as I do. So we have to have rule number 1. There can only be one path into our, what do they call these things? State box. Right? What you said? Sorry. No, they have another SM block, a state machine block. There can only be one input to a state SM block, but there can be multiple outputs to it. So we come in and they draw the SM block using like the dashed lines like I do in your, right when I'm explaining things. So then this would say flow into a condition that is condition on x1, whatever that equation is. And if I get a 0, I want to assert Z2. Okay, so this thing, the dashed lines are SM blocks. So it's just coming down, makes a decision on if I go 0, assert Z2 and move on to this condition. If I have, if I don't have this decision, if I do, it's 1, come down. Regardless, I'm going to move in the X2 and either move to state 2 or state 3, depending on the condition X2. This is all it's going to do. It's just going to build up more and more complicated state machines. One of the weird things with this is that there is no fundamental difference between having something like so I enter an SM block, I come in here, and I, if 0, assert Z1, if 1, do that too. Or, same type of thing, but I could just have them be parallels. These could end up being implemented the same way as long as you converge back these two paths in some way. This does, just because it appears to be in series, it isn't meant to convey timing. And that's one of the downsides to SM machines, is they're not very good at determining timing. The one thing that they do for you is if there is feedback, so like if X2 requires the decision of, if X1 requires the decision of X2, then this, let me erase this second one real quick. So rather than 1 coming here, there's some decision to be made this way. When you draw the SM block, all feedback signals must run outside of the SM block. So feedback has to come back outside. And the reason for that is, to be clear, that this X1 decision is going to be made on whatever the past X2 is, right? So X2 has already been made when I come into X1. And that's to make it clear that we're coming out of this SM block and we have a new input when we make that decision. So that's one of the rules that we need to abide by. This book has lots of rules on the SM charts. There's a small chance of this showing up on an exam at all, but it's something to be aware of. Yeah. And this is where we would use, in real life, we design a state machine to have some sort of reset state. And you make sure your reset state sets everything how you want it to do. And a lot of times you'll turn the system on and just have an auto trigger reset to make sure you know exactly where the state is. Okay, so now that we understand those, I can use them to talk about other things because they're not that tricky. Oh, that's excellent. That means I have like 10 seconds to run and grab my charger. I'll be right back.
Well, I know it's back then.
I know from refrigerators, that's how I know refrigerators. Yes.
So what do you do is you put the flip flop. Like, it's basically it's simple, but it doesn't need like inside.
I don't have to know
I
that.
think like, you know,
I'll tell you what.
If you'd like to pity me further, I came in with a fully charged battery. That's how long my battery lasts, 1 hour and 4 minutes. Okay, so let's have a traumatizing flashback to that multiplier. And we can use a state machine chart. And where you'll see these used a lot, or similar, not necessarily these. Again, I don't use this exact methodology, but you'll see that something like this used everywhere, is in the control logic. So there's two different things that we think about when we design an FPGA. The first is data path. What you guys are working with so far is mostly data path. You're doing something with the data. Eventually, you'll have to build control logic, right, that decides, am I working with switches, or am I working with the ROM? What am I doing with the data A? And so this is the decision matrix. So this is going to be a description of the decision matrix for the add or shift in that add shift multiplier. So, as per, wow, that came out. Yeah, I guess that was. Yep. Yeah. Okay.
Or it might be a different marker.
No, because its cap was off and I was using the purple one. Oh, I was using that one. See, you guys are smarter than I am. I'm just trying really hard to fulfill that stereotype of the scatterbrain professor. And I've come to the conclusion that that stereotype, it's not that it attracts that type of people, it's that the job creates that type of people. It's surprisingly, one of the hardest things of being faculty is like the necessary ability to change thoughts completely, just randomly. Like I'll be working and one of you guys will show up to my office hours and be like, I'm no longer designing a course, I am now programming VHDL. And is it lab 2? Is it lab 1? Is it lab 3? I don't know. Let's see how. So I think that is why I get all scatterbrained. Okay. So in this control logic, I come into the state, right? System turns on, I enter state 0. And the first thing that I'm doing is, should I start? If the answer is no, let's just hang out and do nothing, right? The next decision is, well, if I should start, then I want to send out a load signal. And then we're going to enter a new state. Now that state needs to make a decision. And that decision is going to be based on n, where n is the multiplier bit, right? So if I have 1, 0, 1, 1, this is m at 0, this is m at 1, and so on and so forth. So these bits are m. So it's saying if my first bit is 1, we should add which is an output, go to S2 and second state and shift And then I needed to make another decision. This is really awful.
Where are the dashes?
The dash? Oh, state 2, assert shift.
No, the dashes, like, you know, how you do the dashes around.
Oh, yeah. There's one. This is S2. And shift, SH. So then I need to make a new decision. K is the number of bits. If I've reached K, so I'm going to have some external counter to this that needs to determine K for me. This is just the control logic. I don't need the counter inside of this. Let's just assume that I have access to this variable K somewhere, and we're going to go and look at it. And if K hasn't been reached, then that means 0. And we're going to go ahead and feed this back into, where do we need to go? Back into S1. Right, because I need to start deciding add and shift for as long as I need to until I've reached K, until I've added and shifted all the times that I need to. If I have reached K, I'm going to go to a new state S3 and assert an output called done. We're done with this, and then we're going to feed all the way back to state 0. On the flip side of this decision, one decision is 1. The other one is what happens if I'm 0.
So what is M?
M is, I just erased it. It is the decision on whether, I have to make sure it's one of these two, and I have to remember which one it is. Because you can shift either way, right? Multiplication is symmetric.
It's symmetrical, yeah, it's not.
Yeah. So it's just going to take one of those, and that's going to be M at time 0.
Okay.
And more specifically, it's going to be M at K, where K is 0 to 3.
M at 1 would be 0, right?
M at 0 is 1.
What?
And M at 1 is 2.
Okay.
Yeah. So yeah, so that's what the K decision is based off of. So then M goes into 0, and M0. It's actually going to be very similar, right?
Straight to state 2.
Yeah, we could probably just go straight to state 2, because we still need to shift. They didn't do it that way, but I don't see any reason not to. They went to a state. They go shift, check for kill, done. But I don't see any reason not to go into state 2. Tell it to shift, then check for kill. Yeah, that should work. And that's all it is. And this is control logic. So the big takeaway, I don't need to account for every little bit in this thing. This controls the data path. The data path can do whatever it wants on its own. This is just outputting decisions based on inputs in the progression. So if you draw this, you could take something like this. And if I were to put something like this on the exam, it's way more likely that I provide you one of these and ask you to write me some VHDL based on it. not anything else tricky. Because that's going to be the real skill. Is because someday, somewhere, you will encounter a systems engineer that absolutely loves drawing these things, and he's going to hand you one, and he's going to go make this. That is likely to happen if you work at a big company. It may or may not be this exact notation, because I've seen a bunch of different, and I don't use this one, but they'll all be similar. Same ideas. What's that? Yeah. One and the same sometimes. Okay. Yeah, so it all. Okay. Smooth charts. I think that's this is way too short.
You're a safety. Brown hates that.
Yeah.
Hey, you would be remembered. They would remember.
Yeah. So this is a little bit weird. I guess this is probably good news. Hopefully you guys don't resent me for it. That was all the material for today. That went really fast compared to what I thought it would. But I'm going to hand back your exams now, and we can worry about that. I will get to that after I get this handed out. And I'm sorry, I don't know your names for crap, so I'm just going to pretend like I don't know any of them so I don't reveal who I actually know. Adam. Haas, no Adam. Shane, I don't think he's here. I think he's in the other class. Trevin.
I mean, I don't know you. Well, sometimes I don't think people feel that. I can't pretend to know. One each class. I know the judge, Ryan. Elias. Elias. There you are. What's your name?
What's yours? Justin. I know I've seen your guys' exams. Let me run to the office and see if I just set them somewhere dumb. If not,
If not, I've got you here at home in the back.
wait.
Did you get yours too? Hey, thank you for saying that. I haven't planned with it. I want to know if I got it. That's what I want. You did. Has it started? Yeah, that's gonna be a fun example video.
It's 11 pages. Oh, that's like this cover sheet.
If they're not fun to someone else's exam, then they must be at home. I did all the grading at home over the weekend. I will find them. So all I have is Adam, Shane, who's not in this class, and Taylor, who's not here today. Drives me nuts. I apologize. I did post your exam scores at least, right? No, I don't think anybody missed it. I think everybody has their grades posted. Okay, so I should have brought a blank one, but I'll stare at this one. So what I will say is I'm very happy with the way the exam went. I thought you guys were actually, so as I was walking around looking how you guys doing, I thought you guys actually were doing worse than you were. I think you guys ran into an issue where you were like so nervous you didn't work for a long time. Like, oh no, they're just not going to finish it. But it ended up being the average was 70, like, which is beautiful. The uncurved.
Yeah, that's like where you were in the year.
So 10. Yeah, no, it was a great curve. And it was identical for both courses. Your guys' average percent was actually a little higher than theirs. And a higher percentage of you guys got A's. But the difference was like your guys' average was like 1.5% higher, and your standard deviation was 1 point higher. So like statistically, there's no difference. The high score was unadjusted was 73 out of 75. Lovely. The next highest score was 70 out of 75. 68 maybe. No, there were a couple of 68 and a halves.
Yeah,
And then yeah, so I threw away in all of the statistical analysis. I just threw out the 73 because it was higher than anything else. I think the 68.5 may have been the second highest. So that's why if you look at the actual high score reported, it's 80 out of 75 or something. So I just adjusted everybody by 7, and then he ended up at over 75. So it was not taken into consideration in the curving of this. So any good statistician would do, we throw away the outliers. So all I did to curve it, and the most generous way is just I added 7, so then that curve is not centered around a C, right? It's now centered around a B, roughly. As I said, good chunk of you guys did really well. Exactly. So I'll go over some of these just to point out the issue. Most of you did really well on the first question. It's just drawing circles. I wanted that one to be easy and obvious so that you feel confident for the rest of the exam. The second one, which is the De Morgans, I'm actually gonna, now I'll keep recording the Zoom, it's fine. I told you guys I was gonna use it. So the mistake on De Morgans that you guys did, and I don't really understand, but I will point it out. In the second term of that De Morgans, for some reason, the first step that like a solid third of everybody did was this. and they treated this and like it was inside of the mortgage. If the bar's not over it, don't do it. And this is, the bar is kind of like, well, you can treat it like it's a parentheses. And that's why we use the Morgans, is because we can't do anything inside the parentheses until we get rid of the parentheses. That's one way of thinking about it. So that was like the major issue on that first one. Other than that, it was like little, oh, and the first term, when you had A, B, I'm not going to do the correct bars, A or C, and all of this is barred. The first step that you have to do isn't to turn the inside stuff. You treat them like they're separate terms. Yes, but everybody that did it that way, I think, screwed up somewhere.
I just corrected.
It's just A or B, but I think it's A or B bar.
Oh, wait, okay.
Yeah, everybody that distributed got A and B.
Yep.
I don't know what, I didn't spend time looking through to figure out why, but it was a really consistent error, so there must be something in there. I don't know why. The last issue was, and we already brought this up, that everybody ended up at some situation where they had this and then called that one. Tons of people did that on this question. And it just isn't one, and you can draw a truth table to figure out why. Question number 3 was really good. Question 3, shoot, you want me to just look at your blank again? Okay. So question number 3 was just asking to, given an expression of x equals the sum of 3 and 6, what is the following expression? Question number 4 was a question about Mealy and Moore state machines. This one went really well. Next question was fillets in flip-flops, just like the homework that a lot of people missed, and I pointed out. Most people got this right. There were some minor mistakes, but I think almost everybody got like partial credit on that one. True falses, mixed success on that one. But it was okay. Nothing I'm really concerned about. Number 7, though, kick your guys' butts. Not everybody, but a good chunk of you did sum of products rather than product of sums on that one. And then the next biggest mistake is that people missed that there were zeros in the 4 corners and could function as one large group. If you didn't do that, things got a lot more complicated. But what do you mean?
Can we do it on the board?
Oh, you want me to do it? Yeah.
Yeah, I got the zeros, but somehow got it wrong. The way it is, I stated the single comment that, so as long as it is 0 with the top, it's up some, all out, and it's good. Well, I probably wasted the time on that problem.
I remember. Oh.
Okay. So, starting off, I don't think I'll do the whole thing. But the one that most people missed, right, is this, and that. All the same. If I label this A, B, C, D.
That would be B not B not, right?
Well, let's walk through. So A changes, B doesn't change, and then C doesn't change. Ooh, oops, wow. There you go, that's your turn. because it's product of sums, I'm looking for the zeros. So they are zeros, so they're not bothered.
Yeah, I don't feel like.
Yeah. Right, and this all just comes from De Morgan's. You can also do the sum of product and just do De Morgan's. Yeah, there are a lot of ways that you can solve this. This is the most direct. I wouldn't have done that to you if I had closed book, but you know, closed book means what you mean. If it makes you guys feel better, so apparently somebody like, I don't know, tattled on me to Justin because they were like, his exam was too hard. And so Justin like came to me, sorry, I shouldn't say Justin. I'm talking about the chair, right? Just Dr. Jackson. So yes, so Dr. Jackson came to me and it was like, he was like, I heard it went really rough. And I was like, yeah, let's see, I graded it. And then when I told him what the average and the bell curve looked like, he's like, I don't think I would have even curved that for them. That sounds like a great exam. So he wouldn't have given me the +7. Right? Because it was a beautiful curve, guys. I'm very proud of that. Okay, so question number 8 was, it's just a JK flip-flop. And so what I kind of wanted you guys to see, right, is start by drawing up the box and start going like, okay, so there's an M1, there's an M2, there's a clock, and then you could draw out the enable, and then it had a, what do they call it, out or something. And my strategy is always, and yours can be different, it should hopefully, and for about half the class, I think, got it. I see inputs, I see outputs, I see a clock. Now, I said, name this device. We only know a couple of devices, right? We pretty much know flip-flops, muxes, and ROMs. There's not a lot else we've got going on, and those were only 3 guesses that I saw. I actually liked seeing the guesses when you got stumped and just throw something out there and hope for the best. Big fan of that. And then it was just a matter of looking at what the logic was doing in this, and you could have quickly drawn out a truth table for M1 and M0, M1 and M2, or did I call it 1 and 0, M1 and M2, versus out. And then you would have hopefully seen pretty quickly that was the same truth table as a JK flip-flop. I saw a couple of muxes and a couple of ROMs. The weird ones, I saw some that, what was it? That they don't even, like muxes, they don't even have clocks, right? Muxes aren't clock devices. Well, you can put a clock through a mux, but it's not a clock device. So that was that one. And number 6 was the timing delay one. Just so you guys who don't have it can remember what that one was. So this one, I covered this pretty explicitly in the review. Not this specific one, but how to set these up, right? So the first thing that you do is you see that Z is the only thing that has different paths. So Z has to be the problem. The second step is to set the circuit up in such a way that Z changing will affect the outputs, right? So that means that X has to be 1 and Y has to be 1 because they're inputs to the AND gate. If Z goes into an AND gate and the other input is 0, the output of that AND gate is going to do nothing. Yeah, more than I would have liked, I suppose, had problems. I do not have the stats on.
What was the question of the person about 73 days? He missed 1 on the last.
Yeah, he missed 1. It was 2 different issues where he missed 1 point. And I don't recall what the first one. Oh, no, I think the only other issue, I think he missed 1 point on number 13, which is the other timing diagram one.
Was there any problems that open up that in the
I did not take enough statistics on that to know, especially with the way I graded it. But I didn't. Okay, so this was the circuit. Now looking at this one, we know X has to be, Z is the problem, because it has two different paths that it can go to the output. If it doesn't have different paths, it can't cause an issue. Step two, if X is 0, this output gate will never change, and so we can't see if something happens when Z changes. Same reason for Y. If Y is 0, this output and this AND gate will never change.
So you do those three, the first one is X, and then do those three that, you're about to end that.
Oh. I did start drawing that one correctly, sorry. What it is roughly the same result, actually identical result. So, we know X and Y have to be 1 in order for the gate to react. The next question is, does Z need to be 0 to 1 or 1 to 0? Well, that's harder just to look at. It ultimately doesn't matter, right? In this problem, there's only maximum of 3 gates at 10 nanoseconds pot. It's 30 nanoseconds of drawing, which is 3 transitions, the worst case. I would just take a guess if I were you guys, right? But let's say we go from 1 to 0. We know that this is X and Z bar, and that this is Z and Y. Okay, so the first thing that I would do is draw out the outputs of each of these as Z changes. So, for Z, Z wants to go from 1 to 0. Okay, so to start out, if Z is 1, Z bar is 0, which means we have X and Z bar is true, right? 0, 1, and Z and Y, wait, did I do that backwards? Z is 1, those is, oh wait, sorry, that's 0. Z and Y is true at my time step of 1. So let's start by doing that. X, Z bar is 0, and Y, Z is 1. We know nothing can change until this point, right? So now we go to 0. Maybe we should start with a Z bar in here as well. Just so Z bar is 0, and then 10 nanoseconds later, it jumps up and stays there forever. Right? So Z changed. After 10 nanoseconds, Z bar changes. Similar, because Z bar changed, now 10 nanoseconds later, this AND gate becomes true. So this is our X and Z bar. So 10 nanoseconds, 10 nanoseconds goes high. Okay, great. ZY. So Z and Y starts out as true, but after 10 nanoseconds, because we've gone low, is going to become false. Forever. Right? Now the output That's the bar. Oh, sorry, no. Output, we'll just call this F. When we started, it was 0 or 1, which is true, right? So it starts high. We know it's not going to change just because Z changes, because the soonest that it can change is after 2 gate delays, right? Therefore, after 2 gate delays, we need to evaluate what is this or that. Well, at this point, that's 0, that's 0. Right? So it's supposed to stay 1. Because whether Z or Z bar is true, it's going to be 1. But we get this 1 10 nanosecond window where they are both false, which 10 nanoseconds later propagates to the output, and then they change back, and 10 nanoseconds after that, it's fixed. This is the static 1 hazard. Look good? Makes sense now? There will be more timing diagrams. These are one of the things in this class that are actually used, partly because I do notice somebody struggling in labs to debug your circuits based on looking at timing diagrams. Timing diagrams are like bread and butter for digital engineers because we stare at them for a long time in debugging our circuits. And when you start to see the F is dropping to 0, like you might do a test bench and see this happen. You need to go, it's really a matter of reverse engineering it to figure out why did this happen, right? But stepping through and creating them is a helpful exercise that will make you a better engineer. I'm tinkering with the idea of creating a master's level class that like a quarter of the whole thing is time. It's that important, it really is. Yeah, well, don't get a job in verification.
Well, I'm thinking about like currently right now, I would just be watching your phone like that and try to do that.
Yeah. Okay, so number 10, mixed results, more good than bad, to be honest. Simplified expression using a K-map. Some people screwed up the K-map, which was sad. It made it really complicated, but as long as you drew the gates correctly, you got partial. If you screwed up the K-map, I didn't mark you down for screwing up the next part. So partial credit on this one's easy. Then D asks, if I ask you to change the design system using NOR gates, so instead of NAND using NOR, what simple change could you make at the first step, so at the K-map level, in order to change it, the ease of design from NAND to NOR? And the answer is you just do product of sums instead of sum of products, because that conversion becomes really easy. I was sad to see nobody take a guess at that, because I saw some answers that weren't that were still technically correct. I was like, well, I wouldn't call that simple, but you know what, fine. Like someone said, well, you could use the Morgan's theorem to do da-da-da, and I was like, you know what, yes, you could. That doesn't sound simple to me, but yes, you could. So taking a stab at things is good for your partial credits. The state diagram one, which asks you to detect the sequence 1, 0, 1, 1, 0. Yes, there was a surprising amount of people that just didn't get to it, which was disappointing. And then the next most common, like the common mistake of people that did it, is they had too many states. So what I had grading wise was basically, if you drew the state machine, the state graph and the table, you got 3 points for just drawing the table correctly. As long as the table like looked like your graph, you were fine. You got 3 points for that. There should be 5. So just a quick tip, if you ever have to draw these things, the nice brute force way to do this is start by drawing the detection sequence, right? 1, 0, 1, 1, and then we know we have to do something with 0, but we don't know what yet. So the points that people lost, I marked down 1 point for every 2 connection arrows they missed, and 1 point for getting the wrong number of states. That was all. Straightforward grading. So you do this, you're halfway there, right? And after that, it's just a simple matter of going through each state and seeing, what do I do if it's not met? Well, 0, I hang out. This one, what happens if it's a 1? Yep, I stay and hang out. Right? And this state is done. This state is done. State 2, I got a 1, so I have to do something if I'm a 0. So I got 1, 0, 0. What does 0 do? 2 zeros is nowhere in my sequence. So let's try that again. Next step, all right, so I go 1, 0, 1, 0. Well, I already know I have a 1, 0 somewhere, right? Well, this is a 1, 0, so it's actually state 2. And that was one error I saw a couple of times, but, right, so that's a 1, this is a 0. Let me move this one down here. Okay, so now I do 1, 0, 1, 0, 1, 1, 0. Well, that's my detect. So that's going to be with an output of 1. And we can go back and fill all the outputs out as we need, but we're getting some points. And I actually didn't mark down for those slashes or not, as long as you got the output slash. I was pretty lenient on that one. So I've got 0, 1, 0. Well, a 1, 0 sounds familiar, doesn't it? And alternatively, I can get a 1. So I do 1, 0, 1, 1, 1. So I have somewhere that's 2 1s, right? That's all.
That'll be overlapping. Okay.
Yeah, and I said you would miss minimal points, and it turned out you missed 1 point. I said 2, but it turned out to be 1 if you got the non-overlapping versus non-overlapping. Or maybe it was only a half. It may have only been a half a point if you didn't get the overlapping one. Is it 1? Okay, so, and I was very lenient on grading the state table. A couple of people did try the VHDL architecture to squeeze out some extra credit points. Someone actually did, really close anyways, they missed like a half a point. Number 13 is the trickiest one. This is virtually everyone missed it. Yes, this is the this timing diagram.
Yeah, that's fine.
Yeah, so normally, most of these I had a grading rubric, and then I would go through, and I was grading these one problem at a time, so I didn't even know whose I was grading. I tried to keep it anonymous so there wasn't subconscious bias or anything like that. That's not true. I actually really like all of the students so far. It's been very pleasant. But this one was hard because I created the rubric, and I came in and almost everybody just got 0. And I was like, okay, that doesn't work. So I created an alternative rubric that was a little bit more forgiving, that gave you points. A fair number of you got the points, so the requirement was basically that your flip-flop reacts correctly to the rising edge of X. Right, and I think that's what a lot of you guys missed. is that X is the output of enable or clock. So as long as enable or clock is high, with a little bit of delay complexity in there, right, then X stays high. So X just basically, well, stayed high the whole time almost. There's only one opportunity, and I think I circled it on everybody's exams, and for you that don't have it, I will point it out, where that you have not clock and enable. Not clock and enable. So there's only one window of opportunity. There was one that barely meets the timing at the very beginning of it. That was okay, as long as you clocked it in right. So you look for possibilities of, because X starts high and then it drops low, and it needs to go back high before we clock in any new data. If X doesn't change, the flip-flop output can't change, right? And that's what a lot of you miss, where you were like triggering, I think, like off the negative edge of clock or something weird. Honestly, a lot of you, I couldn't figure out what you were doing. So this is where a good chunk of you got 2 points because you did react correctly to X changing. And then after that, it was, did you get X changing? Right. Then did you get X right? And then did you get output right? And I just ranked that 2, 2, 2. A lot of you got 2 points for that first one. And so 4 of the 7 points of the curve came from this question, because it was rough. And I won't walk through it because it was a little bit cruel to have like the flickering of the enable with that complex delay. I wish I had been stayed a little simpler, but it's okay. Don't feel too bad on missing this one. Almost everybody did.
So Q never goes high.
No, Q stays high. Q is always 1.
So it never.
Yeah. There were options. So Q actually, I was pretty lenient on the Q because you don't know what Q is coming into this.
Yeah.
So I didn't mark down for whether it started 0, started 1, or even had someone that started unknown.
So wherever it starts.
Yeah. Well, no, so it should have clocked at 1 if it started low.
Right.
Shortly after where the arrow is, actually. One delay after the arrow.
One of the half delays or one of the full.
On the clock to Q delay. Yeah. So it's a little ways after that, because that's a longer delay, but. Okay, 14, this was a fun one. I was pretty happy with it. It was just circle 5 syntax errors into idle and start bit. I could tell some people got a little flustered and started circling things that weren't in idle or start bit. That's where most of the questions got wrong, where they're like, well, this is wrong. It wasn't. This code all works. It's simulated, it's synthesized, and it's even implemented on an FPGA fully functioning. And then, so I took fully functioning code and then added 5 syntax errors. What's that? This is going to look a lot like some people's code because this is our lab. Yeah, the only way, there are some people in this class that like to do the if and then they do a then on the other line and then they write stuff on the same line as the then. That particular person would know really quickly if it was their code. Yeah, so. Yeah, so B, I just gave everybody points for. B was not worded well. I did give out a couple people extra credit for understanding. B was, what is the value of the counter when it enters start bit for the first time? What I should have said is, what is the value of the countdown when it first enters start bit when implemented on an FPGA? So I didn't write that question well. Everybody got points for it. Because if you look at the code, it's just, you don't know. That's the answer. You have no idea what that counter is because it's never initialized. Because the big point was that when you declare an integer and then you do this, it doesn't synthesize. That's what I was trying to test, but I failed, so I just gave everybody points. Anything that was extra credit, so whether it was the process or I gave extra credit for this, was not calculated as part of the curve. So I did the curve and then added the extra credit afterwards, so you don't have to worry about that. The last question. This one got everybody but one person and almost a second person. So one person who was off by 1 bit, and I completely understand why. So, what's that? What question? Oh, yeah. It's hard to tell when I can't see mouths. Okay, so assume the code worked up to the point it leaves stop bit for the first time. The transmitter that the receiver is getting data sends 0, 1, 0, 1, 0, 1 at time equals 0. The second packet is transmitted at t equals 1 second and contains a byte block. What value does the receiver report as the contents of the second packet? So what I wanted you to do here is start stepping through the code to try and figure out what it is doing versus what you think it should be doing, right? You know, and this is why I use our lab, is because we know what it's supposed to do intimately, right? And so what happens is we go through idle, and I said it worked. So let's just assume that it worked. So it goes all the way until stop bit. And if we know, and I took away data so you guys didn't have to worry about any of the code in there, because if I didn't do that, you might have to look at data or stop bit to see if like there's a trick there. So I took away data to keep it simpler. There was another hint in that I said there was 1 packet at t equals 0 and 1 packet at t equals 1 second, right? That's a hint that nothing happens for a really long time. So the second packet doesn't actually come into play at this at all. I also was a little bit nice in the first packet that it sent was started and ended with a 0 to make it a little bit more obvious. Apparently didn't help. The issue is, if you look at stop bit, you enter stop bit at, what did I say? 1/4 of baud through the last bit in the byte. So the last bit is 0. Stop bit is 1, right? So I said you stop here. At this point, it enters stop bit, okay? 1 100 megahertz clock cycle later, it enters idle, right? Because there's no countdown in my stop bit. So instantly, basically, enters idle compared to the slow baud rate. Once I enter idle, what is the condition in idle to leave idle? Well, we go back, we look at idle, and idle says, if S data is 0, let's start receiving another bit.
Also, this is like exactly what mine was doing.
So 100 megahertz clock cycle later,
Yeah.
it's now right back into start, where it then waits half a clock cycle to wait for the stop bit to be over, right? Or to center itself. And then it waits 1 full clock cycle in order to take the first bit. So it waits here and then samples. Well, this, because it takes 1 second before this changes, goes on forever as far as this system is concerned. So it goes stop, idle, start, 1 1 1 1 1 1 1 1 forever. It will actually